Hello, everyone, and thank you for attending today's webinar, Low-Dose EBSD Analysis of Beam-Sensitive Materials. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all questions. A copy of today's slide deck is available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon in the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce the presenter for today's webinar, Dr. René Decloux. René has been working as an application specialist for EBSD and later also EDS at the EDAX European Support Office in Tilburg, the Netherlands, since 2001. His focus is on instrument demonstrations, conference and workshop presentations, and after-sales customer support. This includes on-site trainings, assistance with analytical problems, and scientific collaborations. Although focused on Europe, his work has brought him to customers and conferences all over the world. This international travel is a great bonus for his hobby, geocaching, where he tries logging at least one cache in every city he visits. As he's always been fascinated by the physical world around him, René has chose to study geology at Utrecht University with a specialization in materials science from a geological perspective. René's first introduction to electron microscopy and microanalysis came during his undergraduate thesis on deformation and pressure indicators in natural fault rocks from New Zealand, which involved a significant amount of SEM and TEM work. Later, during his PhD thesis on nanometer scale melt structures in upper mantle rocks, he also learned about high-resolution TEM imaging and EDS analysis. Around this time, he also started using EBSD on a system without any automation. René's background in geology gives him a slightly different view on materials research, which has proven invaluable over the years at EDAX. In geology, one must look at a material without any prior knowledge on how it was formed. Applying this view to man-made materials can be a great help in explaining unexpected test results or materials failures that customers need to understand. Now over to René.
Well, thank you very much, Jonathan. Welcome everybody to this webinar on low-dose EBSD analysis of beam-sensitive materials. So what am I going to talk about today? Why would we want to do low-dose EBSD? Because we have very fast cameras nowadays. We can go very, very fast, thousands of points a second. But to do that, you need higher currents, bigger beams to give you some signal. Not all materials can accept those kinds of beam conditions. So you can look for improved lateral resolution when you make the beam narrower, so low current analysis. And it also opens up a new range of materials that have been extremely difficult to analyze before. So beam-sensitive materials where the crystal structure get easily damaged. Now, what do we do to enable that? And the main thing that opened this up is direct electron detection. It allows measuring with very low currents, low voltages, and very gentle beam conditions in general to study your materials without damaging them immediately. But before we go there, we need to have a little think. Can we just go as low as we like? I call it here. So how many electrons do we need to actually see something in a diffraction pattern? Can we just go to a few picoamp and still expect diffraction patterns? So what is the minimum dose that is required? And then in the end, I'm also going to talk a little bit about some examples on improved lateral resolution in metals, and mainly the last bit is on beam-sensitive materials. What kind of information can we get from these materials when we are really reducing the beam currents that we use. So let's start with a quick introduction in how the direct electron detection works. This is with the clarity detector. That is the direct electron system from EDAX. And during the development, one of the things we wanted to do is provide a detector that was extremely sensitive and completely distortion-free. So to do that, we had to remove the optical path. So there's no phosphor screen, there is no lens system, and the electrons are coming directly onto the sensor, which means there's also no distortions introduced during the signal detection. Now, direct electron systems are not new, of course. They've been used for many years already, and mainly in transmission electron microscopy, biological analysis, and it's also for beam-sensitive materials, very fast, very sensitive sensors. And a number of years ago, it has been demonstrated to work for EBSD applications as experimental configurations. And some of the problems that people ran into at the time was the sensor. It was sitting on a printed circuit board, and that geometry just made it very, very difficult to put it in the microscope chamber in the geometry that we need for EBSD and to get close enough to see enough bands to get reliable indexing. Another issue was the temperature. These sensors can get quite warm, and when they are sitting directly on a printed circuit board, you have some minutes, maybe tens of minutes, and then it just cuts out because it gets too hot. Now, on the clarity, we have designed a system in the traditional EBSD geometry, so you can just mount it on the normal EBSD port on your scanning electron microscope, and it consists of multiple chips, so it's a multi-chip system with a single top sensor. So that means that electrons hit the front of the detector, and then they are going to be transmitted into one of those 4 chips behind it, giving this 512 by 512 pixel resolution. And a very important thing, this design also allows for efficient cooling to take the heat of the sensor out of the microscope vacuum to the back of the detector. Now, this is an in-chamber view of what it looks like. On the left, you have the tube for the EBSD detector with the sensor on the front. All the electronics are inside the tube, and there you have the sample sitting at 70-degree tilt. Now, when you hit the sample with the electron beam, diffraction happens, hopefully, and then these electrons are going to hit the top sensor, and there is a bias voltage over that sensor. Electrons are pulled down into an amplifier and into a next step comparator that just measures how many, what the signal is, so what the voltage is that was coming in. We cut out the noise, and the read noise is very, very low on these systems. So anything below 3 kV is just cut out, but above there we can get EBSD or electron signal, and that effectively means that we can count single events. So single electrons coming into a pixel on the chip can be reliably counted. Now, the nice thing of these detectors is that we have a lot of gray levels to work with. So the bit depth of the sensor has about 11,500 levels, so 11,500 events that we can store. That means that we have a very large range of intensities, and that is very handy for EBSD patterns that have a very large intensity gradient from very bright in the middle to very weak at the edges. So it allows you to grab very high quality patterns if you fill all the wells on the chip, and you can really see small variations and high detail levels in your patterns. But also, because there are so many levels, we can also just select a very small number of them and work and stretch that, so we can work with extremely weak signals for high sensitivity. and that will allow us to go for low dose. So just to illustrate what that looks like, here I have a pattern where on average in every pixel we have about 5,000 electrons. And you can see there's a lot of detail in the pattern. The highest intensity was in the middle towards the edges. You have fewer electrons, which means there's less contrast, but all the details are there. You can also see in the profile here, there's a lot of information hidden in those patterns. And if we don't want to fill the whole chip and we want to go for very low numbers, low intensity, then here is a pattern where we just use 10 electrons on average per pixel. If you look at the profile, it's just noisy, but you can just make out some bands in there, and actually for the indexing algorithms, that is enough to get reliable indexing. So we just need a few patterns, a few electrons per pixel. And just to illustrate what that looks like, here is a sequence of patterns at 10 kV with a few hundred picoamp, and indicated here is the exposure time. So at the bottom left, we have 20 milliseconds, and that on average, the maximum electron dose, it says here, is 50. So not very many electrons, and we get that in 20 milliseconds. And we just go to the right, it's just longer and longer exposure. You see how the number of electrons increases. But you also see that already in 50 electrons, you have detail in the pattern. So it's not just noise. You can already see detail inside the bands, and that just gets stronger and stronger. If we go to 20 kV on the same material, we get more signal, more electrons, and you can also see here what happens. If I just go to the next set, just increasingly filling the wells on the sensor to show all the small details inside the bands. And this gives you fantastic quality diffraction patterns that you can use, for example, for cross-correlation applications, or also for crystallographic analysis in combination with simulations. Now, the main question for me here for low dose is, how low is low? Can we just go as low as we like? So let's try that. This is a sequence of dynamic simulations where we're not trying to get a very nice pattern, but where we are going to see how many electrons do we really need to get a recognizable diffraction pattern. The top left pattern here, it says 1/16th. So that is the average number of electrons per pixel. So it's 1/16th of an electron per pixel on average. So most of the pixels have no signal at all. And there's just a few pixels out there that have one or a few electrons, and that's already enough to see the bands. Then you go to 1/8, 1/4, half, and the second to the right on the top row is 1 electron per pixel on average. And that is already enough to get a nice quality diffraction pattern. Now, what you have to keep in mind for this is that this is a simulation of the diffracted signal. So this only shows the intensity of the electrons that diffracted on the bands that show us the bands. There is no background in these images. And so if we look here, again, average 1 electron, maximum we have about 10 electrons per pixel, here at the bottom in the middle of that zone axis. That looks plenty to index. It's easily recognizable. But if we look at an experimental pattern, here we have 40 electrons, and the maximum number of electrons anywhere in this pattern is 50. So it's the same difference from 1 to 10, so it's a 10 electron difference, but 40 of those are just background noise. These patterns, or this experimental pattern and also this simulation, that suggests that we can get diffraction patterns in a few tens to a few hundreds of picoamps, depending on the material. If you look at a three-dimensional plot of the image here on the lower left, you can just see a very noisy display, but you can recognize the bands over there. And again, that is very recognizable. So this is enough information to get reliable indexing, but it requires good patterns. So the material has to allow you to get this signal to noise or this band signal on top of the background. And when we do that on a good sample, this is on a steel, and then we can just collect EBSD data with 13 picoamp. So you can work with very low currents, very narrow beams, where we just have 10 electrons on average per pixel in the entire pattern, and we can get good results. Now, the next question is this signal over the background. So how many electrons do we get in the diffracted signal, and how much is background that we are removing? Because normally when we do EBSD analysis, the software will do a background processing. So we are taking an average over many grains, we get the intensity gradient, and we remove that from the pattern. And when you do that, we get beautiful patterns, we get good contrast, and if you look at it in a 3D plot, you can see all the little details like spikes in here, and the bands are clearly visible. It gives us good patterns to work with, but it obscures this signal-to-noise ratio that we're after at this moment. So let's take a look at some unprocessed patterns. And here's one from silicon. You can see the brightness in the middle. There we can see the bands very nicely, and towards the corners it gets a lot darker. And when I look at a three-dimensional plot of that, we don't have the spikes. It's a very smooth intensity gradient, and the bands are like painted on top of this intensity gradient. So maybe 5 to, in some cases, up to 20% of the total signal is diffracted information that we can use for indexing. Between 80 to 95% of the electrons are just background noise that we want to remove. So that is something that we have to keep in mind when we are going to drop the current. The other thing to keep in mind is this band to background ratio is very strongly dependent on the material. Here I have some examples from very light materials, beryllium, and then we go progressively heavier. So silicon, iron, platinum, gold. And you can see on the beryllium, the bands are just almost painted on top. They don't really stand out. And if you look here for the platinum and also the gold, then the bands are clearly showing some topography in this plot. So they really stand out over the background, which makes them so much stronger to work with. And any materials that are very light, so it doesn't have to be a single-phase metal, of course, can be silicates, it can be semi-organic materials. You have to keep in mind this ratio of the diffracted signal to background. When we just do a dynamic simulation again, only of the band intensities, with the same number of electrons in a simulation, you can already recognize the contrast, the brightness of these bands. So left the beryllium, to the right the platinum, where we have much more signal. And just imagine that that signal is superimposed on the background. These simulations also allow us to quantify that. This is with about 900 picoamp, so that is an indication of the electron dose as function of the voltage. And here we have the backscatter yield. So of course we have a higher yield with a higher atomic number, but you can also see that we have a drop in backscatter yield, so in backscattered electrons, when we lower the kV. That, of course, translates into increased exposure times. So on the right, it's effectively a flip of that same plot. So how long do we need to measure to get the same intensity? And then you can see that for beryllium, for example, you need about 3 times the exposure time as that we have for platinum under the same beam conditions. And here is just to illustrate that in the exposure time needed to get 50 electrons per pixel on average. And then again, so it's about 3 to 4 times the exposure time that you would need for beryllium. And the lower the kV, the worse it gets. Now, if we look at the patterns, so this is a sequence for beryllium 10 to 30 kV. We can see the contrast more or less the same. The variations in intensity that you see is caused by the topography on the sample that I had. So there's for silicon. Again, the contrast is almost the same. You can just see that the bandwidth is much wider here on the left at 10 kV than here on 30 kV on the right. And there's iron, platinum, and gold. So all of these appear to have about the same contrast. But when we look at how long we need to measure that, I hope you can read it. In white, superimposed the exposure time that's required. For gold, at 10 kV, we would need about 490 milliseconds. And for beryllium with the same beam conditions, 1.3 seconds. So again, about 3 times the exposure time. And again, that also goes for equivalent materials with similar backscatter yields. Now, those were simulations. Then let's take a look at some real measurements from the patterns I just showed. Again, this is about 900 picoamp, and I just increased the exposure to get 90% central illumination. No, you don't have to go so high, but this was just to get good quality patterns that we can compare. And you can see that from 30 to 20, there's almost no difference in exposure time. To 10 kV or 15 here, it drops a little bit, and at 10 you need a lot more. Now, this effect is a combination of the efficiency of the detector. There's a bit of a dead layer on the detector, so that you have to punch through. So that has some of the effects, but a more important effect probably is the specimen surface. The lower the kV, the lower the penetration depth. So any contamination that you may have on the surface is going to dramatically affect how many electrons actually carry diffracted information and that can come out. Now, just to illustrate, that was the dynamic simulation. And we can see that on the true measurement, it goes up a bit. And that was that combination of the detector efficiency and the specimen surface. If we just calculate that to density instead of just atomic number, then again, it goes up a little bit with lower atomic numbers until you reach the very low ones, here beryllium, it gets very high. So if we look at what the patterns look like actually for silicon platinum under these conditions, here we have 1 millisecond exposure. For 900 picoamp, we get 6 electrons on average for silicon and 8 for platinum. And you can just see how that increases to 50 milliseconds. There we have about 300 for silicon and 390 for platinum. So the number of electrons is not so different, but the contrast and the number of bands do change. We can improve that, of course, when we do a background correction. The 50 millisecond patterns look very, very similar, and we just make out the patterns at 1 millisecond exposure. And then when you do an averaging there, it gets a little bit better. Of course, it takes a bit more time as well. But we'll get to this type of averaging later on in a technique that we call NPAR. That is something similar as what we see here. Now, having said all that, so looking at the direct electron, looking at how many electrons we need to get the data, some examples. And let's start with some metals. So, of course, you don't need low dose for a material like this. You can just blast it with a high current if you want to. But if you minimize the beam current, In this case, I used 200 picoamp at 30 kV. You get very sharp maps. So it really, the interaction volume for EBSD in this case seems more limited or determined by the beam diameter than it is by the accelerating voltage. If you then look at the other images that you can collect, these are some Prius images that we collect at the same current. When we look at the intensity at the bottom of the detector and we just sum that up, don't look at the bands or anything, just look at the intensity and make a map of that, we get a map where we can beautifully see all the orientation contrast and topography. So all the gaps here between the grains in this cold pressed powder are shown. Then here in the middle, Prius center, that also shows orientation contrast, but it's less sensitive to subgrain structures, so we can see the whole grains a little bit better. Prius top is sensitive to backscatter contrast, so in this case it's not the most interesting chart or map because it's effectively single phase with some gaps where we have some resin. But that would show in a multi-phase sample, that would clearly show where the different phases are sitting. Then, because the beam is so narrow, we get very sharp maps. It also allows us to get beautifully sharp kernel average misorientation maps. So the changes from one grain to the next, or one subgrain to the next, can be defined very sharply, very much detail. Better detail than you could with a big beam. Here's another one. This is deformed platinum. Again, just a few hundred picoamp, a few millisecond exposure. That's enough to get good diffraction patterns for reliable indexing. Again, we get a very sharp EBSD map, the image quality map on the left. And when we look here at the deformation, just zoom in a little bit, then here you can see beautifully the low angle boundaries that are between 0.5 and 1 degree here on the left. And here in this blue grain on the right, those boundaries are between 0.05 and 0.2 of a degree. And you can nicely identify those. Okay, then let's take a look at some more challenging materials. Here I have an example of some perovskites. The pattern you see here on the right is one of those perovskites. This is methylammonium lead iodide. And here we have pretty nice patterns that we can index very well. But that's on a nice flat sample. The sample I have here is it's inorganic, so we don't have this methylammonium, but it's a lead halide perovskite. And this is an ITO substrate with a coated layer of perovskite that was then sintered. And you can just see like this flower-like radial structures. And in there we can sort of recognize, yeah, like feathers growing out. Looks a little bit like dendrites. And question here was, can we see what the crystallographic makeup is of those clusters? Are those single crystals? Can we recognize these dendrites in there? So how was that formed? Now, this was measured with 10 kV and about 200 picoamp. I have to say the sample was provided by Dr. Julian Steele from University in Leuven in Belgium. And when we look at the patterns, first thing, of course, to do is see, can we get patterns at all and can we index them? And in this case, yep, we can get these patterns. We can see all these bands. In the software, we can load the expected structure, and then we have to, you can interactively add or remove bands as you can see them. Which bands are visible exactly also depends on the composition of the material. So depending which spots in a unit cell are occupied by a heavy or a lighter atom will affect which bands are shown. So you can interactively modify which bands to use for indexing. And then during mapping, we can store all the patterns, or you can just move your mouse over the material and see what the patterns look like everywhere. That's what I typically do when I get an unknown material. I just want to see a few different patterns to confirm that everything I get can be indexed in a consistent way, that I know what phases are present. And in this case, I just had a single phase material, so I could index all the patterns with the same structure file. And this is what the IPF map looks like, the color map on the right. The sample is highly topographic, so a lot of the deeper lying structures don't have a free line of sight to the detector, so we're not going to get anything there. Those are white. But interestingly, all those flower-like structures index with a uniform orientation. So there's no dendrites, there's no original crystals growing in different directions anymore. The sintering completely recrystallized all those grains. Interestingly, if you then look at the texture, of course there are not that many grains, but you can recognize in the inverse pole figures here that the structure is not random. We can see like there's a line, a band of points here, but away from the 010, and here we have a very strong band of points from the 001 to the 010 direction. When we color code those pole figures based on the IPF coloring that you see in the map, you can just easily correlate the grains with the points in the inverse pole figures. Now, then let's make normal pole figure plots. Now this becomes much clearer. And here you can see that almost all the grains have the B-axis sticking out of the sample. So it's almost like a coarse fiber texture, where the B-axis is coming out, the A-axis is going all the way around, and the C is, it's shifting a little bit. But the A-axis has a preference of being in the plane of the sample, and the B-axis has a preference of sticking straight out. So that was a really nice result on this material. Then here's another example. This is some analysis taken from the paper you can see here on the lower right, from Steele et al. From earlier this year. This was an S-cast material without the sintering, and you could see these clusters of fibers. And also there the question was, can we say something about the crystal structure? And yeah, these grains are a little bit small, or these patterns, but what you can see is when you hit the tip of those fibers with the mouse, with the electron beam during analysis, you can actually grab diffraction patterns of a rough topographic sample like this. Normal mapping will never work, but you can, just by finding just the tip, the edge of those fibers, you have enough diffracted signal to get those bands. In many cases, the automatic band detection will allow you to get an indexing result. In some cases, like here, let's say on the top center, there the bands are very weak, but we can just recognize them, and manually you can just draw them in and get an orientation display. And we can also plot these in a pole figure, and they show very, very similar distributions as those sintered areas that we saw before. So in this case, it's the A-axis that is just around the corner. So that is the growth direction, let's say, of those fibers. And the C is clustering a little bit more in the middle. So also on a sample like that is very beam sensitive, after grabbing a pattern, that part of the fiber was just gone. It was enough to get valid information about the microstructure and crystallographic orientations. Now then, another class of materials that can be very tricky for EBSD, biominerals. And one of the reasons those are so difficult is because there is organic material in between the grains. And when you hit that with the beam, the organic material will disintegrate and effectively coat the sample right next to your beam, and then you lose all the diffracted signal. So just as an example for that, this is a cross-section through a brachiopod shell. And here you can just see on the top left in the image quality map, it's all gray. You don't see a lot of detail. You can just make out a few slightly larger whitish grains, but you don't see a lot. And in the lower right, we have some IQ values here where we can recognize, the orientation. In the IPF map, that's directly seen as well. You can get an indexing result in the lower right half of the map. In the top left, there's nothing there. We could not go to higher currents. We could not wait longer because it would just disintegrate the material. So what we can do then is we can collect the map, store all the patterns, and use a tool that we call NPAR, Neighbor Pattern Averaging and Reindexing. Now, what that does is we get a pattern. This is actually one of the good patterns. So we can now make out the bands. It's by no means a beautiful pattern, but it's very indexable. And then we can do almost like a moving average, where we take the pixels around this pixel, get the patterns from there, average those 7 patterns together on the hexagonal scanning grid that we're using, and then index that resulting averaged pattern. And when you do that, the signal to noise ratio dramatically improves. So in this case, you can see the noise in the original pattern and a lot more detail and clear bands in the indexed pattern, or in the final pattern. And that is very indexable. If we look at the very weak area in the top left, there's almost nothing visible in the original pattern. But after NPAR, we can actually make out a few bands. And in many cases, that is sufficient to get an indexing result. So just to illustrate the effect, here we have the original map. And where did that go? There is the result after the NPAR processing. So you can see that the lower right half is almost fully indexed now. We get a beautiful representation of the structure, but also in the top left, you can see the crystals around those black areas. Those are actually organic conduits through the structure, and you can see how the crystals go around that. Then the next one, the interior of a shell. So here we have a few hundred picoamp, 15 millisecond exposure, 12 kV. Again, much higher was not realistic. It would just damage the material. And here we can see on the inside of the shell, we have calcite pillars on the lower left. That's where the muscle of the animal was attached. And towards the top right, we get the smooth nacre surface of the inside of the shell. And what I try to analyze here is a transition from the pillars to the full nacre coverage. Okay, so when I index that, we get these nice colors. Everything is red in the aragonite nacre, and here on the calcite pillars on the left. And in between, we have a very fine-grained zone with some different colors, some bluish materials. And when we separate those, this is the pattern quality of the calcite. So we can just see how the calcite is underneath those early aragonite crystals. Here on the top right, we get nice aragonite patterns. But in the middle, this is this transition zone. That's the quality of the patterns that we can get during original indexing. When we then apply NPAR, also here, it really improves the signal to noise and allows successful indexing of all these patterns. And that gives us this full map where we can actually study the transition zone. If we look at this image, this is a Prius image here on the left. It shows a topography. It's a Prius bottom image. And you can just see where the aragonite starts growing in between the calcite pillars. You can actually still see the pillars underneath the initial aragonite layer before it's completely covered by the larger platelets. And if we look here on the right, we have a detail map of that area where the large pillars are calcite, and in between we have those orangey red grains you can see that are looking bent down into those gaps between the pillars a little bit. That is aragonite. And when I just separate that out, here on the left you have a phase map, so you can recognize where the aragonite crystals are. And on the right is just the indexing of the aragonite. Now, of interest here is that you can just make out in a little bit deeper between the calcite some organic material. So that could damage when you hit it with a high intensity beam. And it also looks as if the aragonite crystals just, bent into those channels or maybe fell down, perhaps during specimen preparation or over time. But the interesting thing is that almost all those grains show red. And that means that they all have the C-axis sticking out of the sample. So even if the grains are bent inwards into these gaps, you can see that the orientation is already the final orientation that we also get in the nacre. Okay, and then the last example, this is a material I recently also wrote a blog about this one. It is doing EBSD on a garden snail shell. So I'd looked online, tried to find some more information, couldn't really find anything. So just say, okay, what can we learn from this material? And here on the left, there's a cross section through the shell that's ion milled using the Gatan PEX unit. And here you can recognize two main layers. You have a base layer here, that's the inside of the shell, that looks like a crossbar structure with some columns. And then there's a fine-grained cover, and on the top there's this dark, thin layer. That's an organic coating that has the color of the shell. Now, everywhere I can get a pattern in that structure, it looks like that, and everything is aragonite. And already this is an interesting thing, because aragonite, of course, is the high-temperature polymorph of calcium carbonate, and these snails somehow manage to grow the aragonite at ambient temperatures. So that's already a very nice example of biological control of the crystallography. Then that was a cross section. Now looking from the top, at some places I could peel off the colored surface, and that allows me to get an EBSD map of the surface. And here we have these, on the right we have a little zoom of that larger map. We can recognize the individual grains and those featureless dark gray areas. Again, that is organic material that you don't want to damage. When we index this, everything goes red. So also here, it's a very strong organic control of the crystal direction. And interestingly, in the shell we just had, the aragonite forms little platelets, and that's the smooth nacre that we're all familiar with. And in the snail, they're just very small grains, but they don't form the same dihedral crystals on the surface. But the orientation is the same. So it's the C-axis coming straight out of the shell surface. Now, when we have those individual grains, we can of course also look at the other features of the microstructure. In this case here I have a grain size map. Blue are the smallest grains, in red are the largest ones. They're highlighted here in this chart on the right, with the average grain size around 1 micron. And then here I had a chance to look at a cross-section. This was an oblique fracture through the entire shell. So on the lower left here, you can see this crossbar structure. And towards the top right, it's the surface that we were just looking at from the top. Now, there's a lot of topography, so I couldn't get a lot of indexing in the lower left part. But you can see whatever I could get, it's all red, orangey. So it's all outward oriented as a Z-axis. So both the small grains and this columnar material. But if you look at the in-plane orientation, it's very different. Now these are two very distinct layers crystallographically, where in the columnar zone, I have almost a 90-degree rotation with respect to the grains on top. And inside this columnar area, we can also recognize two different orientations. So if you zoom in, we have this on the lower right, we have this magenta color and a dark blue. They both have the A-axis, as you can see in the top left pole figure, parallel. Oops, sorry. There's that parallel, but there is a very well-organized rotation of about 30 degrees, as you can see in the Z-axis orientation, between the two different directions of those columns. So it was a very nice result on this type of material, just to see what you can get and what you can learn about beam-sensitive materials. And just to summarize that, with the direct electron system, we can get very low noise patterns. We can work with minimal beam currents, minimal numbers of electrons. And from the simulations and the measurements, we can see that on average, we can already get good indexable patterns with only 10 electrons per pixel. What you have to keep in mind is that low density materials, light materials, require longer exposure. They have a lower backscatter yield, so also lower intensity in the diffraction patterns. And you have to find a sweet spot between the backscatter yield, which is a function of the material, but also of the KV, and the exposure time and when it starts to damage. And that will be different for every material, so it requires a little bit of experimenting. When you have a material that is not sensitive, you can still go to a higher KV, but very low currents to get very sharp maps where the step size then really exceeds the interaction volume. You get very sharp interfaces between grains and structures. And when you have to use the low current beam conditions, you can get very stable measurements of beam sensitive materials like perovskites and biominerals. So I want to conclude with that. Thank you very much for your attention. And are there any questions?
Yes, Renee, we had a few that came in. On slide 5, how does the velocity camera compare to the results shown with the clarity?
If I go back to slide this one,
yeah.
The velocity camera has a few different imaging modes where for the highest speeds we use lower bit depth to allow for the faster processing. And you can get the spec is up to 12-bit, so you can get a lot of intensity levels already. But it's a bit less than here, and a bit of a problem is the noise that is generated in the phosphor screen. So you can get similar numbers of gray levels that we can measure, a bit less. So I said 12-bit maximum, but it will never be as sharp as those.
Okay. With regard to slide 17, what program was used to simulate the patterns?
These patterns, these were created by my colleague, William Lent. And the basic functionality is part of the OAM matrix module in OAM analysis. So you can get the basic simulations in there. Some of the quantitative things I've shown are not coming from there, but this type of analysis you can do with OAM matrix.
Okay, and a quick follow-up to that one, is NPAR available in Team?
Yes, NPAR is available in Team. It's an optional feature that when you have collected the map and you have stored all the patterns, then you can reopen the map, and when you have NPAR available in user interface, you'll get a little checkbox that allows you to reprocess it using this NPAR technique. So it is there in the newer Apex software. It's not available in the Apex user interface. It's completely taken over by the functionality in OAM analysis, where we have a lot more control over which points to reindex and what to do exactly with the image processing.
Okay. Have you tried using the clarity for pharmaceutical materials?
I have, and the main problem for that is the polishing. You need to have a crystallographically clean surface. That means that when you cut the material or you break it, you have a very rough surface, and you have to remove that information. I am experimenting a little bit with the PEX. I have some samples lying here. So I think it should be possible, but I don't have any examples at the moment. One thing to keep in mind is that the material needs to be crystalline. A lot of the things I've seen are not fully crystalline. There may be more polymers that don't have the longer range ordering that we need to grab EBSD patterns. But yeah, it's something that I'm experimenting on.
Okay. On slide 47, in regards to the shell, it's a very brittle material. How are you able to prepare a flat sample out of it, including the use of ion milling, without distortion or damage for getting good EBSD patterns?
Yeah, it is indeed. It's a very brittle material. It was actually so brittle that it broke of its own, and I could use the fracture surface to look at the surface of the material. That was just a little bit that broke out that I could just glue onto a stub. The ion milling, I mounted a small fractured bit vertically on a blade for the PEX and just shot through. So there was no mechanical interaction or force applied to these materials. Interestingly, if you look at, if I go here, this map, this was unpolished at all. The only thing I did here was peel off the organic top layer, and this is what I got. So there was, I think if I would try to improve the pattern quality or the surface quality here, I would actually destroy the material.
Okay. The next question, is it possible to record Kikuchi patterns at 1 to 2 kV acceleration voltage?
No, that's going a little bit too low. There's a few reasons. In the past, I have collected patterns down to 2 kV, but they are extremely weak. And at the moment, for the clarity, the noise threshold is at around 3 kV. So that's where we limit it. It is something that I also have been experimenting with. I have been able to get good diffraction patterns at 3.5 kV. So we're pushing the limit to go a little bit below that, which is almost impossible with a phosphor screen. because it doesn't produce much light at those low voltages. But yeah, up down to 3 kV I've been able to do. But much below that, not really.
Okay, I think that's all we're going to have time for today. If we didn't get to any of the questions, we will answer them via email. Renee, thank you for this excellent presentation, and we hope to hear from you all soon. Take care.